Assalamualaikum warahmatullahi wabarakatuh. So my name is Ibrahim Nachim. We'll explain about the simulation for exercise 1 for lab MSSE. I am from the group 2, section 6. So here is the lab. So for the exercise 1, we will simulate about increment and decrement at the path 7. So here is the model of the PSS from Simulink. So and this is the area 1. So the area 1 you can see here. This is the path 7. So for the initially for the path 7, the value is 900. We can see here it's the 907 million watt, and the result is so initially the result from the Simulink is the 967 million watt, and then we try to run it. So this is the initially of the simulation. We need to see the stable case. So here is the stable case. We can see on here the stable case, and then we will try to simulate again, but change the resistive load value at the path 7. We try to increase the value in here. So 5,000. Right, we try to increase. We want to see if the generator can supply or not at the 5,000. Here we try. Oh, sorry, we need to run it in. And so actually, our group have done the exercise 1, and we have our group have already run it. And the first step is we try to increase by percent, which is the 20%, and then we up again to 30%, 40%, and so on until reach I think 1,400 million watt. We try to stop because it's still the result is still same. It's still a stable, and then we try to increase with a more large value. Increase, and then the value start not stable, so we choose 5,000 and we attach to the lab report. So here this is the result of the path 7 for the increment. As we can see here, it stopped at the time 1.499 seconds. And it is because the supply of the generator cannot support the bus because it's too large of value resisted. So that is for the increment, and then for the decrement and alright, so this is for the increment. For the increment, our group has increased and see the lab report first. Yeah. For the sudden decrement, our group has decreased the value from 967 million watt to 483.5 million watt. So we will try to run to which is okay or not. So this is the one 400 400 483.1 483.1 5 5 okay, and then try to 9. So here the result. Okay, running. And now it stopped. Now the simulation stopped at the 1.790 second. We can see it goes to up there, and it stop here, it stop here, and it stop here. So this we can see our group has discussed, and we try to brainstorming why this is happening, and then we found the note from internet, and we discuss about it. Why we get this after we decrease the value, and then our group says that maybe there is the PSS system has the rotor angle stability, and then you need to synchronize the operation. So in case if we decrease the value of the load at bus 7, then it occurs due to voltage instability. So that is the reason why we get this result. Okay. So that's all for the bus 7. Thanks.
Hi and a very good day, Doctor. I'm Karthi Puspanathan with a matrix number of DE 2001 and 01. So I'll be demonstrating the experiment 2, which is all about sudden increment and sudden decrement to bus bar 9. So bus bar 9 can be seen at area 2. So here is bus bar 9 and here is bus bar 10 and so on. So any increment, decrement or initial value can be observed here. So the initial value is 1667 megawatt. So I've already generated the outcome, so I've edited a bit. So this is the outcome for 1767 megawatt. So it shows a stable system, because this experiment is all about whether the area, back to the MATLAB, this experiment is all about to identify whether the system will be stable or not stable when a sudden increment or decrement happens. So initially the system is very stable, where it takes some time to be stable, where it takes 14 seconds to be stable. So the output voltage and output voltage, the angle, the rotor's angle, rotor's power amplifier, everything takes 14 seconds to be stable. So initially the system is very stable. So I'll try with increment. So I picked the increment of maybe like 3000, nearly like 100% of increment. Yeah, what? So check the take some time to compile it. So here's the value. So here's the graph. So just now we saw it shows a full stable, where it reaches the stability at 14 seconds, but now it trips out. It never show any graph, and it just become unstable nearly at nearly like 0.5 seconds. It just took 0.5 seconds to trip out, because the generator is able to produce 1767, but we are like putting it over trouble, where we increase 100%, nearly like 3000 so it couldn't give us reach a stability. So I'll back to the MATLAB and try it for decrement. So decrement, I'll try like maybe like 500. 500. Back to the one and run it. So here's the graph. So the graph took 1 second to flip out. So the system is unstable. So the system is only stable when the parameter is 1767 when the initial value. So a sudden increment, decrement, the system becomes unstable. So that's how the area to 11 buses system works. So thank you, Doctor.
A very good morning to all the lecturers who is watching this video presentation today. My name is Lezin Zhou, and now I'm going to present with you about the result and analysis part for exercise 3. So the first one is about bus 8 temporarily board 3-phase fault, and here is the block parameters for a fault. And the system discipline first appears as transient board 3-phase fault at bus 8 because of the breaker switching time has been elected. And the simulation results are therefore helpful in examining a variety of stable and unstable circumstances, so including steady, moderately, and somewhat unstable example from 0 to 20 seconds. So here is the graph we get from the MATLAB, and the 3 color boxes indicates the 3 different state for the result. So the first one is unstable case, which is indicated as the red color, and the next one the next one is marginally stable, which is state as the yellow color, marked as the yellow color, and the last one is the green color, is the stable case. So for the unstable case, the variables like rotor angle, speed, voltage, magnitude, and electrical machine power are in unstable state from 1 to 3 seconds, and the temporarily fault at bus 8 occur at 1 second. And for marginally stable, observe all the values are heading towards equilibrium and attempt to reach stability at 3 seconds towards 10 seconds. So at stable, everything even out in a straight line as the system enter equilibrium state once more from 10 towards 20 seconds. And the next is the bus 8 permanently about a 3-phase fault. So here is the parameters. And when the switching time of the breaker was changed, the system is first interrupted by a permanent about 3-phase fault at bus 8, and however a short circuit prevents the system from operating fully for 20 seconds. Because of this, the simulation output helps in 2.5 seconds to examine a variety of stable and unstable circumstances. And here is the graph get. So for unstable case, which is indicated as red as the graph before, so it's at the back of the graph, and the variable of rotor speed, voltage, magnitude, and electrical machine power enter an unstable state at 1.1 second and continue to do so until 2.5 seconds later. So in contrast, for the variables remain constant while the other two increase, which is the rotor motor. So for the marginally stable case is indicated as the yellow color, which is at the center of the graph. So the system was trying to stabilize itself before the permanent board 3-phase fault detected, and the fact occurred at 1.1 second in the graph above and shown in the yellow color. And last is the stable case, which is indicated as the green marking, and we can only observe the variables. The rotor angle is in a stable state from 0 to 0.25 seconds. Now all these other variables such as rotor motor speed, voltage, magnitude, and electrical machine power are unstable from the beginning. So next will be the bus 5 temporarily about the 3-phase fault. So here is the MATLAB system. So the system discipline first appeared as a transit board 3-phase fault at bus 5 because of the breaker switching time has been elected, and the simulation results are therefore helpful in examining a variety of stable and unstable circumstances, including steady, moderately, as before, and from 0 to 20 seconds is also same with the bus before and the condition before. So here is the graph obtained from the simulation at MATLAB and indicated by red, yellow and green, where the red color is shown the unstable case where the temporarily brought 3-phase fault at bus 5 occur at 1 second, and the variables like rotor angle, rotor speed, voltage magnitude and electrical machine power are shown to be in an unstable state at 1 to 3 seconds. And the next is the yellow color, which is the marginally stable cases. All the variables are attempting to attain stability at 3 to 11 seconds and moving towards an equilibrium state of operation. So the last is the stable case, which is indicated as the green color, and the waveform observed has been straight out from 11 to 20 seconds. And before the problem at 1 second, the system was stable. The next one is the bus 11, temporarily brought fault, where here is the condition, and when the switching time of the breaker was changed, the system was first affected by a transit board 3-phase fault at bus 11, and however a short circuit prevents the system from operating fully for 20 seconds. Because of this, the simulation output helps in 2.5 seconds to examine a variety of stable and unstable scenario, including steady, marginally stable and slightly unstable examples. And here is the graph obtained from the simulation. So for unstable case, which indicate by the red mark at the center of this graph, so the system enter an unstable condition between 1 and 1.25 seconds after the bus 11 had a transit board 3-phase defected, and the marginally stable case is indicated by the yellow color, where we can see the system is striving to correct and adapt appropriately to establish an equilibrium state of operation. Solve to reach stability from 1.2 seconds and onwards as indicate a yellow marker. And last one is stable case, which is indicated as the green color. So that's all from me. Thank you very much.